Hey, everybody. Audio okay?
All clear?
All right.
Yep, sounds good.
Happy Monday night to everybody. Happy How the Crap Does Homework 5 Work to everybody. Okay. How's everybody doing? Yeah, thanks, Jay. How's everybody doing? By the way, I got called up tomorrow again. I think it'll be the last time. So I got to either do the regularly scheduled tomorrow lecture on Wednesday, or I could do it tonight after this. And I'm helping myself to decide with this ice cream. Any prefs on that?
Flip a coin.
I can rock and roll. I can keep going, just wrap it up and I can go tonight. After we
Well,
do
I
the
was
help
joking
section.
that you should flip a coin and decide based on that.
Well, yeah, that's true. I can, but I'd rather be more or less scientific depending on how you view it. Okay, but if any of you guys would rather stick around and be the studio audience later on tonight, and that would be tomorrow's 2810, that might tip me just a little bit toward doing it. Homework 5. All right. Here we go. Boom, homework 5. What I really wanted to focus on was these last 8 questions, or the ones that I think are causing a little bit of distress. Does these ring a bell to anybody?
Yeah, I did those on the homework and the exam. I think I had them figured out, but probably not, given that you decided to schedule a homework help.
Well, you might have been smoking it, I mean, you could have been. I don't know. We'll find out, though. So there's a handful of things that I think have been kind of common, I guess, common struggles in understanding this stuff. The other thing I need to do is let me get the slides from, is it 4 or 5? It's got to be 5. Well, they both have it. So we're okay. It is the Mondo Cool picture of the MAR, MDR, the memory thing. So I've got that. Okay, got that ready to go. Yeah, so what I realized is that when we were doing everything live, in the classroom, this was something that I think typically just became a topic on the whiteboard. There was just a certain amount of whiteboard time that we haven't had. And I think I realized that it wasn't being covered as directly. I mean, it's all there. Everything you need is in the slides and in the book. But let's walk through this. And what I want to do is, we can do the first one, but I want to just, the goal is not to give you the answers for the homework, which also won't help you directly on the exam, right? If you don't know what you're doing. But the concepts are gonna work. First big concept in all of this, there is a slide. Where is my slide? About Ks and megs and gigs and terabytes. Which lecture was that in? Anybody remember? Zach, you remember?
No, I do not.
Come on, man.
I'm sorry.
I mean, I can do it again. I can do it on my Majike whiteboard right here. Let's just do that. Okay. but there is a slide for this. This first part becomes relevant because if I say there's 32 gig, 16 meg, where are we at? Okay, 1K. 1K approximately. 1K is approximately 1,000. Okay. A K is approximately 1,000. K for kilo, right? Like kilograms, kilometers, kilometers, aka 1,000 meters. Okay, that's the decimal system. Now it turns out that we use these terms that we borrow from the metric system, but they are only approximations. Okay, 1K is 2 to the 10th. Which is exactly 1,024. Okay, so that's first reminder. Okay, 1K is about 1,000. It's 2 to the 10th, and it's exactly 1,024, which you can do by simply taking 2 to the 0, and which is going to be 1. 2 to the 1, which is 2. 2 to the 2, which is 4. 2 to the 3rd, which is 8, and you just keep doubling it every time. If you do that 10 times, you're going to get to 1,024. Okay. Then the next thing that comes up is a meg, which is approximately 1 million. All right. I'm not going to draw the whole 1 with 6 zeros, but 1 meg is approximately 1 million. 1 million is 1,000 times 1,000. So in other words, it's 2 to the 10th times 2 to the 10th. And this is something, there is a fair amount of struggling with the algebra that is a prereq for the class. There's a lot of kind of core algebra struggling. I just want to say that in part so that you understand, if that's you, that you're not alone. But 2 to the 10th times 2 to the 10th equals 2 to the 20th. Here's the principle, okay? If I have some base like 2, and I've got 2 to the, say, n, and I'm going to multiply that by 2 to the m, if the bases are the same, then I can just add the exponents. Okay? So that would equal 2 to the n plus m, whatever that is. Okay? Put this another way. If I said 2 to the n, and I multiplied that times 2, like that one right there, just 2 to the n times 2, well, 2 is the same as 2 to the 1. I dropped my highlighter. It's not a highlighter. It's a big fat Sharpie. Okay, right? So that's going to be 2 to the n plus 1. Okay? Let's do this with a little bit of other intuition. Let's just take, if the base is 10. Okay? Let's do it if the base is 10. If the base is 10, and you have, like, say, 10 to the 3rd, which is 1,000, times 10 squared, right? 10 to the 3rd times 10 squared. 10 to the 3rd is 1 with 3 zeros. 10 to the squared is 1 with 2 zeros, right? So that's the same. Oh, thank you. Thank you for the slide. Right? That's the same as this problem, right? And the way you do that, you may recall, is you just add up all the zeros, right? You can do it that way. The other way to do that is just 10 to the 5th. 10 to the 3rd times 10 squared is 10 to the 5th. I'm just adding the exponents. Jerry there, right there. I'm just adding the exponents. Okay? That's a little bit of the intuition in base 10. But the idea in base 2 is exactly the same, okay? So, all right, yeah, thanks, Zach, for dropping that on there. So 1K, in fact, can I... No, I can't really blow that up. Maybe I can do it this way. There, no, that's not what I was trying to do. But we did get to see the meme there from Jay. I need my... Zach, what lecture was that in? Yeah, caught red-handed. What lecture was that in?
That was chapter 3, digital logic structures.
Chapter 3.
Slide 105.
All right. Must have been a little interlude. Slide, wait. No, not slide 105. How about slide 90? In any case, it's right there. Okay. So the idea here is that 1,000 times 1,000 is 1,000,000, right? 2 to the 10th times 2 to the 10th is 2 to the 20th. If you're confused about, the way in which you can add the exponents, then it's going to be a problem. But I will just remind you, number one, let's learn it if you don't know it. Number two, knowing it is actually a prereq. So it's one of those things that, we can kind of assume that you have, that you have it, that you know it. K, a meg, a gig, and a terabyte. So it just keeps going up by a power of 10. Sorry, by an extra, by a power of 10. 2 to the 10th, 2 to the 20th, 30th, 40th. Okay? And this is approximately equal to 1,000, 1,000,000, 1,000,000,000, 1,000,000,000,000. Okay. So the reason that we throw that out there by way of review is the fact that when we start off over here and we say a computer has 32 gig of RAM, okay? When we talk about how many megs of RAM, how many K of RAM, how many gig of RAM, we're talking about how many bytes are in memory. That's all we mean. RAM is random access memory. We're talking about how many bytes in memory. Addressability refers to how many bits or how many bytes are at every one of those address locations. 16 bits equals 2 bytes. This is really good, by the way. And it's my dinner pretty much. So, ice cream for dinner, baby. Salud. Okay. So if a computer has 32 gig of RAM, how many bytes does it have, right? And one of the things that the question asks is how many memory addresses are in this computer and how many bytes are stored at each address in memory. All right. Now it turns out that the second question in both of these is the only one that's directly given in the statement of the question. Okay? How many bytes are stored at each address in memory? That is the definition of addressability. Okay? That is the definition of addressability. So if I say the addressability is 16 bits, that means there are 2 bytes at every location, at every address. So I was talking to Zach. Zach had a great, I've had some tried to come up with examples. Zach had a really good one that I really like. If you got an apartment complex, right? And every apartment complex, let's just say it's uniform. Every apartment has like 4 bedrooms, right? And they're private bedrooms. So there's like, one person in each bedroom. And there's 4 bedrooms in every apartment, right? The addressability is going to be 4 people at one address, right? At that one address in that one apartment, there are going to be 4 people. That's the addressability. Period. I mean, that's it. So in the same way, if I've got an addressability of 32 bits, I could also say I have an addressability of 4 bytes. But if I have an addressability of 4 bytes, that means that at every memory address, there are 4 bytes there. Okay? Now, if I've got an addressability in your apartment complex of 4 residents at every address location, and I told you that there were 100 apartments in the complex, how many residents? If everything's full, what's the capacity? Well, independent of full or not, what's the capacity if you can put 1 person in every bedroom? Tracking me here? I got 100 apartments. I got occupancy of 4 people.
400 is just your maximum.
Right. The maximum would be 400. The actual number of bedrooms is 400. Right? So if this were memory, I'd have 100 memory addresses, and there would be 4 bytes at every memory address. How much total memory would there be in the system? 400 bytes. Ta-da! And if instead I told you that there were 400 bytes of memory, and the addressability was 4 bytes per location, per address, how many addresses are there? 100. You know, that's just simple. Again, that's just algebra. That's simple algebra, you know, where you're just going to kind of, you know, the inverse relationship between multiplication and division. Okay. So when you look at this right here, the first question is, the second question, how many bytes are stored at each address? It is given to you right there, 2. It's 2 bytes, aka 16 bits. All right, everybody cool with that? Now, the next thing that's actually given to you pretty directly, is how many bits are in the MDR. Okay, the MDR is the memory data register, and this was the one I wanted to drag over this picture that you love so much. Okay?
I'm going to cry.
You're going to, yep, exactly. Me too. The MDR is the memory data register. Anything coming out of the CPU and into memory is put in the MDR and then latched into memory. Anything coming out of memory comes out of memory and gets, you know, and latched into the MDR and then sent over to the CPU. The size of the MDR has to match the size of each location in memory. Remember, it's the loading dock. It has to be the same size. Stuff comes off the truck of a certain size, it fits, it gets on the loading dock, which fits, goes into the warehouse where it fits. It has to be the same amount, same size everywhere, okay? So as a consequence, the MDR, which is the memory data register, also has to be the same size as what you store at every address in memory, which is the definition of the addressability. Okay? So in this example here, the addressability is 16 bits. So how many bytes are at every address? 2. And how many bits are in the MDR? 16. Again, 2 bytes, 16 bits. How many bits are in the MDR? Okay? So half of these questions relate to just that simple issue of addressability. Okay? And then this one here, it's byte addressable, means that there is 1 byte at every address in memory. So how many bytes are stored? Okay, here we go, trick question time. There's 1 byte at every address in memory. How many bytes are stored at every address in memory? 1. How many bits are in the MDR? Enough for 1 byte to come in and out of memory. It's exactly the same, okay? So that's always going to be the same. Everybody cool with that? And being help section, I'm just going to roll, but if you have questions, just stop me if there's something that's not quite making sense. Okay? All right, everybody cool with that? That's the addressability and the how many bytes are at each address and how many bits are in the MDR. This one here, how many memory addresses are in this computer, right? If there are 400 people in an apartment complex and the apartment complex is full and there are 4 one-person bedrooms in every apartment, how many apartments are there, right? I told you there were 400 people, 4 to an apartment. There are 100 apartments, okay? So how many memory addresses are in this computer? So I'm telling you that there are 32 gig of RAM and the addressability is 16 bits. Okay?
So we
Yeah.
just divide the total RAM available by the addressability. Do we need to account for like the list of all of those addresses and subtract that from the total amount, or am I overcomplicating that?
You're overcomplicating it. Yeah,
Okay.
there is no list of all those addresses. You give me a number, and that's an address, right? You give me, like in the LC3, you give me a 16-bit number, and I can treat that like an address, right? Does that make sense, Chris?
Yeah, it does.
If we all remember the decoder.
If you remember the decoder,
Module 3. Module 4. I think it's module 4.
no, it really is the same as the decoder that we talked about. The only challenge is whether that's a happy point of reference. You know what I mean? Whether you're going back to that is like super happy, or whether it's like, no, that's actually more confusing. That's the risk, right? Okay, so how many bytes are stored at each address? Blah, blah, blah. Sorry. This number 11. How many memory addresses are in this computer? Well, there are 32 gigabytes, okay? 32 billion bytes of RAM. And there are 2 bytes at every location. So, how many locations are there?
Is it just 2 billion?
Nope. Overcomplicating again.
Oh, it's 16 billion.
Yep. Right? We could also go, Johnny has 32 billion apples. Right? Should we do this? It really is just that simple. I'm not trying to be insulting with Johnny has apples, okay? But let's do it. Johnny has 32 billion apples, and Johnny has these little packages that will hold 2 apples each. How many packages does Johnny need?
It's just 16 billion.
16 billion, right? He has 32 billion apples, 2 apples in a package. I need 16 billion packages to hold all my apples. That is question 12. Sorry, 1. I keep wanting to jump ahead. That is question 11. How many memory addresses are in this computer? How many packages? How about this one? Johnny has 10 billion apples, and each apple gets its own individual wrapper. How many wrappers does Johnny need? I don't know. What's 10 billion divided by 1? He needs 10 billion wrappers. Okay, that's the answer to the second one. It's not 10 billion, but I'm just saying it's byte addressable, which means every apple has 1 wrapper. Okay? If the addressability is 16 bits, or 2 bytes, then every wrapper has 2 apples. If it's 32-bit addressability, every wrapper has 4 apples. Okay? Now, to get yourself a precise answer, though, this is the part where you got to come back to the first thing we talked about. 32 gig of RAM, that's approximately 32 billion, but it's not exactly 32 billion. And the answer is 16 billion, addresses, but not exactly. So let's do it this way. We got 32 gig of RAM, okay? That is the same as, so the question is, that's 2 to the what bytes of RAM? 2 to the what bytes of RAM is that? Well, I know that 32 is what? 2 to the what? Bueller? $32 is 2 to what? 2 to the what? Come on, I'm waiting.
It's just 2 to the 5th.
Yeah, exactly right. So that's 2 to the 5th. And what is a billion again? 2 to the what is a billion? What is it?
2 to the 10th.
Wait, 2 to the what?
2 to the 11th.
Oh,
kidding.
I'm gonna you're just torturing me now for no reason.
I'm a vindictive person.
Yeah, okay. Again, a billion is 1,000 times 1,000 times 1,000. A K is 2 to the 10. A meg is 2 to the 20th, and a gig is 2 to the 30th. So there's 32. So there's 32 gig is 2 to the 5th times 2 to the 30th bytes in the system. So how many bytes is that? This is just back to your algebra again. 2 to the 5th times 2 to the 30th is 2 to the 35th. That's how many bytes there are. Okay? Now the question is, if I've got 2 bytes at every location, and I've got 2 to the 35th bytes, how many locations? First of all, the intuition is that the number of locations is this number divided by 2. Okay? If I have any number like 2 to the n, and I want to divide that, if I take 2 to the n and I divide it by 2, what do I get, no matter what n is?
2 to the n minus 1.
Right on, baby. Like that, 2 to the n minus 1. Okay? So if I've got 2 to the 35th bytes, and I've got half that many locations, because there's 2 apples in every wrapper, right? There's 2 bytes in every location. Then I've got 2 to the 35th divided by 2. So let's do it this way. Following our pattern, 2 to the 35th divided by 2 is 2 to the 34th. So the actual answer of how many locations is 2 to the 34th. Or approximately 16 billion, but not exactly. All right? Everybody cool with that? And the process is exactly the same on every one of these. Okay, last question. How many bits are in the computer's MAR? Okay, let's go back to our von Neumann picture here again. There's the MAR. It is the memory address register. It is I guess it's about as big as I can make that without blowing it all the way up. Okay, there have to be enough bits in this memory address register to reference every one of these locations. And I've got 2 to the 34th locations. So how many bits? This is a homework / exam question from earlier modules. Okay? If I have 2 to the n locations, also known as addresses, okay? 2 to the n locations or addresses, how many bits do I need to get to all of them? What say you? Let's do a brute force example that's smaller. Let's go 2 to the 3rd. Okay, 2 to the 3rd. How many is that? How many?
Exponent, right? You need 3 bits to represent that total number of values.
Yep. So if I go 1, 2, 3, 4, 5, 6, 7. Okay. So hang on. Okay, right? That's 2 to the 3rd. That's like brute forcing the memory, right? I got 2 to the 3rd memory locations, right? And the addresses themselves are the numbers 000 through 111, from 0 to 7, right? There are 8 of them. 2 to the 3rd is 8. So how many bits do I need to represent each address? The answer is right here. The answer is 3 right there, right? I need 3 bits. When I've got 2 to the 3rd memory locations, I need 3 bits to reference each location. So if I have n locations, how many bits do I need to represent an individual address?
N bits.
Prize money for you. Okay, so that's that relationship that we were talking about like very early on when we first started talking about the number system, okay? So going back to the question, I've got, once I figure out that there are 2 to the 34th, where am I? Once I figure out that I've got 2 to the 34th individual locations, right? And I'm like, okay, how many bits do I have to have for the address? How big does every address have to be? And the pattern is exactamundo the same. Pattern is exactly the same. I don't know if you can see that. Pattern is exactly the same though. I got 2 to the 35th, I got 2 to the 34th locations. N is 34. How many locations, how many bits do I need? I need N. I need 34. Okay? So in the case of this first question right here, how many memory addresses are there? We already said there was 16 billion, or 2 to the 34th. How many bytes are at each memory address? 2. We were given that. How many bits in the MAR? 34. At least 34. Right? How many bits are in the MDR? 16. So it's only 4 questions, but there's a lot of concepts that are kind of like, wrapped up in all of that and kind of intertwined, So that's part of why I think it trips a lot of people up. It kind of synthesizes all of those ideas. If you glossed over them, hoping that they would go away if you didn't pay any attention to them, then you're really struggling right now. If you, kind of figured those out and took the time early on to finesse that and to master that, then it's putting those pieces together, in a way that makes some sense. Okay? That's it. How am I doing on time? That's about a half hour.
Yep.
Any questions or things that are not making sense on that?
So 12 is just the addressability.
You mean question number 12?
Yeah.
Yes, that's right. And the same with 16.
Right.
Yep.
And then MDR is also just the addressability.
Yep. Exactly.
11 is just total RAM divided by the addressability.
Mm-hmm.
And then MAR is just the amount you need. Is the exponent of the number you need. Okay, it's the exponent of the 2 power that equals the number of memory addresses.
Yep. Exactly. And here's the thing. The reason that I double back and I give you dumb little examples like 2 to the third is that you can grab the intuition at that level. You can brute force the intuition. You know, you don't have to. This is not one of those things where you should have to memorize, and remember the big equation. It's the kind of thing where you're just like, well, look, if there are 8 memory locations, that's 2 to the third. I can brute force all the addresses. The biggest one is 111. So I'm like, I can do that with 3 bits. Oh, 2 to the third and 3, the 3 and the 3. I like using 3 instead of 2 because you get 2 squared and then you get 2 on the top, 2 on the bottom, and you lose track of what's what. But, when you get to 8, 2 to the third, it's pretty clear, which one's not a 2, right? So that's why I tend to brute force things with 2 to the third or 8 because it differentiates a little cleaner in the head. And when you go to like 2 to the fourth, it's too big. You know what I mean? Trying to articulate. But if you did, you could articulate it and go 0. You'd like go, okay, from 0 to what? 2 to the 16th. Or sorry, 2 to the fourth is 16. So it'd go from 0 to 15. Oh, that's 4 bits, just like you do with hex. And then, once again, you're at 2 to the fourth, and I need 4 bits. 2 to the 3, I need 3 bits. 2 to the n, I need n bits. Okay. All right, everybody cool? And whether you're cool or not, does everybody get it? And if you don't get it, are you willing to say anything about it? And I'll still be around. Vlad, Zach, will also be around to bounce it off, and But again, it's kind of practice. You've got to burn the time to gain the fluency.
Speak now or forever hold your peace. People.
Speak. Yes. If anyone knows any reason why these problems should not be engaged in, speak now. No, actually, you can also speak next week, but I recommend you speak now-ish rather than waiting. Okay, that's all I got. That's the help section. The rest of these are really straightforward. If you understand the other concepts we've talked about with the dumb little sample data here, it's pretty straightforward. And I think, Zach, I don't think we're getting as many, deep problems with 1 through 10 on this homework. I don't think so.
No, not really.
Okay. All right. I'm getting rid of that, and I'm getting rid of that. Okay. Anything else, you guys? Anything else for me? Because I got stuff to do. But the other question is, anybody interested in sticking around for lecture later on? If I do tomorrow's lecture now, Or should I wait until Wednesday? I don't think I should wait till Wednesday. I think I should do it tonight.
If you do it now, it's already done.
I know. That's the thing. That's the thing. Okay. Yeah. I won't do it right now. I'll take a couple of minutes, but I think let me come back. I'm going to do it at 7:30. Okay? I'll come back at 7:30 and kick back in. And we'll do the 7:30 to 8:45, and I'll send out an announcement to everybody in case again, it's on YouTube, so everybody can watch later on, so no big deal. And if any of you that are here who were the live studio audience want to stick around, great. If not, I'll get like Vlad and Zach, heaven knows they need help, and we'll have our live studio audience. Or I have my friends, if it comes to this.
What's an op code again?
Zach?
It's just
Zach, so help me. Okay.
Wait, the op code
like
is
rubber
back,
duck coating.
right?
Okay. I'm gonna wrap up. I'm good, right? We're good?
Offsite is 1,000 bytes.
Yeah. I gotta take Zach out and I don't know, muzzle him or something. We gotta figure this out.
A byte is 11 bits, right?
It's actually, here's the funny thing. In data communications, in certain kinds of data communications, a byte is 10 bits.
That's dumb.
No, it's not dumb because you got to have start and stop bits.
Mm-hmm.
Okay.
Once you take a network class, bytes just become whatever.
And that's part of the reason I'm telling you that bytes are whatever they need to be. You know what I mean? Because it's not as uniform as we want it to. It typically is, but there's a lot of scenarios in which it needs to be something else in the moment. So, okay, I'm going to cut loose then right now. I'm going to stop the stream, and I'll reload in about 15 minutes for lecture whatever we're on. Okay? Catch you guys later.
Sounds good. See you then.